Hello, everyone. My name is Vincent Lostanlen, and today I'll be presenting Energy Efficiency is Not Enough Towards a Batteryless Internet of Sounds. This is a joint work across two teams from LS2N Centrale Nantes CNRS, the signal processing team and the real-time systems team. My co-authors are Antoine Bernabeu, Jean-Luc Béchennec, Mikaël Briday, Sébastien Faucou, and Mathieu Lagrange. This paper began as a thought experiment, namely, what would a fully autonomous acoustic sensor under $100 look like? To be clear, by fully autonomous, we do not only imply that the sensor should run embedded machine listening software, as opposed to merely transmitting all recorded audio to a distant server. In fact, this is only one of the dimensions in which a sensor can be said to be autonomous. It's what I propose we call the computational autonomy of the sensor. For reasons of privacy and reliability, we'd like to implement algorithms in distributed ways, that is, on the edge, on the network, and not on the cloud. A second dimension is the energetic autonomy of the sensor. We want to be able to deploy anywhere, including off the conventional electrical grid. Think a rainforest, for example. In other words, our sensor should be self-sufficient in terms of energy. Now, the crux of the matter for this article is that no source of energy on Earth is both renewable and permanent. Think solar, wind, piezoelectric, and so forth. All of these shut down uncontrollably multiple times a day because of clouds passing or winds varying in speed. The most straightforward workaround against intermittent power supply is to introduce a rechargeable battery between the energy harvesting module and the CPU. But this design jeopardizes what I would call the operational autonomy of the sensor, that is, the ability to operate for multiple years with minimal human intervention. Indeed, the current generation of batteries is typically limited by a lifespan of a few hundred to a few thousand cycles. The reason why this thought experiment matters is that mass production of electronic hardware poses a fundamental threat to ecological sustainability. Like any other system of information technology, the Internet of Sounds contains non-biodegradable materials and consumes electrical energy. As an illustration, these two photographs shows an e-waste center near Accra in Ghana, where hardware is burnt and disassembled with insufficient safety or environmental considerations. The implications for our field are clear. We should embrace digital sobriety by manufacturing fewer objects while making them more durable. So regarding the Internet of Sound specifically, here's a list of some of the most frequent elements found in electronic waste. On one hand, batteries contains metal from period 4, some of which are highly toxic, manganese, cobalt, and nickel. Audio connectors are plated with precious metals, such as platinum, palladium, and gold. Lastly, microphone parts consist of rare earth materials, such as neodymium and dysprosium. Of course, evaluating the environmental impact of any given commercial product would require a complete life cycle assessment, or LCA, which should encompass the extraction of these raw materials at the so-called cradle, as well as the recycling and or disposal at what is called the grave. Of course, this is by no means simple for a single piece of audio hardware, let alone for the Internet of Sounds at large, and to be clear, this is not our ambition. However, it remains possible to take action at the local level of product engineering. The logic is as follows. The pressure of demand at the cradle and the outflow of e-waste at the grave are both consequences of the volume of goods shipped at the factory gate. So if our products are consume less of these materials, then we can ease out the entire process. Now, let's look at some existing solutions for remote acoustic sensing, and let's stress their limitations. First, the Song Meter product line by Wildlife Acoustics is arguably the industry standard. The SM4 is the model with the longest autonomy. Its weatherproof case encloses 4 D cells. According to the manufacturer, this energy supply translates to an autonomy of 510 hours, either continuously or divided in short acquisition segments over multiple months. Then there are smaller, less autonomous versions of the song meter, the SM Mini, 210 hours, and the SM Micro, 150 hours. And all of these products are above the 100 price tag anyway. So these devices are very practical for short-term research surveys, but they are not autonomous in the sense that they don't make any computations on the edge. They don't have connectivity. And they run on batteries, meaning batteries needs to be replaced every so often. Further on the energetic autonomy dimension, one successful example of a real-time acoustic sensor with built-in energy harvesting is the Rainforest Connection Guardian. Rainforest Connection is a non-profit which aims to detect the sounds of illegal logging in the forests of Ecuador, Indonesia, and Philippines. And the Guardian comprises a repurposed smartphone which again does not perform any feature extraction nor sound event detection on the edge. Instead, it transmits compressed audio to a central server via quad-band radio, typically 2G, 3G. So even though the Guardian runs on repurposed smartphones, this design choice comes at the detriment of ecological sustainability for other parts of the sensor, batteries and solar panels in particular. Indeed, smartphones have a relatively high electrical consumption, especially when transmitting audio data over 2G. To keep the smartphone powered on a 24/7 basis, the Guardian must be able to recharge quickly and retain 40 watt-hours of energy, assuming 4 hours of sunlight per day, hence the need for a large battery and 8 solar panels instead of 1. Finally, on the computational autonomy dimension, a recent publication by Cerruti and co-authors offers inspiring examples of real-time audio classification on the edge. The authors have trained a deep learning model on top of a pre-trained audio embedding to classify urban sounds and have integrated the resulting classifier onto a low power and low complexity MCU, in this case an IRM Cortex. But a shortcoming of this approach is that the resilience to power losses remains undiscussed. The data corruptions which may arise during power losses will affect the response of the RNN, recurrent neural network, when the power supply resumes. This issue is all the more serious when designing off-the-grid, say, solar-powered sensors, because the energy that's provided by solar panels is, again, intermittent and typically fluctuates depending on time of day, weather, and season. Now, let's take a look at our proof of concept, keeping in mind that our final application goal here would be to deploy bioacoustic sensor networks. To recap what we've seen so far, there's multiple generations of sensors. One is the song meter, which purely runs on batteries. Then is the Rainforest Connection Guardian, in which a solar panel recharges the battery, and then the battery powers the hardware. And finally, the works of Cerruti and co-authors, which is really interesting because it runs on the edge, but again, is dependent on the grid. In our case, we want to keep the solar panel design, but do away with dependency on batteries. For this experiment, we've opted for this CPU, the MSP430x 5994, a 16-bit microcontroller with a clock frequency of 16 megahertz, which is sold at approximately $4 per unit. The printed circuit board also features analog to digital conversion and a low-energy accelerator with a standard library of signal processing routines, such as the fast Fourier transform. So the originality behind this microcontroller is that it has no flash storage, but 2 types of random access memory of RAM. 8 kilobytes of static RAM and 256 kilobytes of so-called non-volatile RAM, NVRAM. So of course, the 8 kilobyte static RAM figure is a strong constraint for edge computing. But at the same time, we should note that there's a growing body of research on extreme compressions of machine learning models at the kilobyte scale, with some successful applications in keyword spotting. So this suggests that the limitation does not necessarily preclude the development of batteryless machine learning systems in the near future. So the MSP runs on ferroelectric RAMs, in our case, a PZT, lead zirconium titanate ceramic compound. By applying an external electric field on PZT, one may reverse its spontaneous electric polarization and thus write digital information in a non-volatile way. So in comparison with flash, FeRAM, Ferroelectric RAM, has a much faster access time, and crucially, it has a much higher endurance. It allows over 10 to the 15 read-write cycles, hence a lifespan that is expressed in decades. Finally, let's take a look at some of the demos we've been able to present for this paper. So this is not, of course, a final product. It's only a proof of concept, but only to demonstrate that it's possible to run non-trivial machine listening software without any batteries. We took a sine wave as input and ran a DFT, discrete Fourier transform, on this wave, on this input, to map it to the Fourier domain, and did peak picking in order to estimate the fundamental frequency, and of course got the correct estimate. We know that this estimate is relatively robust to noise, even though, again, this runs on fixed point arithmetic and not floating point for reasons of efficiency. This is what happens with 6 dB of uniform random noise and now 9 dB. And you see that the argmax of the DFT modulus is correct. Now, in case of power loss, an intermittent computing system must retain its execution context. And so this is enabled automatically in the MSP via an approach called checkpointing, in which the state of the program is checkpointed onto the non-volatile RAM so that the context can be resumed later. We show that it's possible to forecast power losses via simple linear regression of the power voltage. Here you see that there's the measured voltage of the supercapacitor and the linear regression, and they basically overlap. This opens an avenue towards embedded power management system in which computations are either launched or deferred, depending on their level of priority and checkpointing payload. So there's here some interplay between signal processing and intermittent computing. To conclude, we've seen that batteries hinder the durability and ecological sustainability of wireless nodes in the Internet of Sounds. Against this problem, we propose a research agenda towards solar-powered acoustic sensors without any wires nor batteries. And our proof of concept is the only one to meet all criteria for sensor autonomy: computational, energetic, and operational. First, it performs a non-trivial machine listening computation, in this case, a short-term Fourier transform. Secondly, it can be paired with an energy harvesting system such as a solar panel. And thirdly, and perhaps most importantly, it is both wireless and batteryless, and thus incurs very little maintenance. Every part lasts for at least a decade. Now, the obvious drawback of our proposal is that these sensors cannot guaranteed to operate on a 24/7 basis. So therefore, they should not be used in safety critical systems. Again, they might shut down at any moment if the energy harvesting goes down. Yet we contend that some applications in conservation bioacoustics or urban bioacoustics perhaps are well suited to intermittent computing on the edge. Future research will gauge whether the idea of a batteryless acoustic sensor network manages to push further the practical sustainability and reducing the material and energetic footprint of the Internet of Sounds. Thank you.